Okay, so today the big topic is something called combinatorics. Okay, this is one of the areas I studied in grad school and as an undergrad intensively. Combinatorics, think of it in simple terms, it's counting techniques. It's how to count. And I don't mean, well, I'm pretty good, 1, 2, 3, 4. No, it's how to count really, really big things. Huge things that you couldn't do by hand. You know, numbers to the sun and back length. Huge things counted simply because they're situations. Let me give you a simple example. How many have ever played poker? Yeah, so I'm going to deal you 5 cards. No wild cards. That's little kids play with wild cards. You know, grown-ups don't play with wild cards. They play with just the poker cards. So if I was going to deal you 5 cards, how many possibilities do you think you have that you could get? Well, the answer would be a lot. Well, what if you wanted to calculate every possible? I'm going to give you 5 cards. If I swap one card out, that's a different set of 5, isn't it? Right? It's not the same 5 cards. How many ways do you think you could be dealt 5 cards? You want to guess? Just if you had to guess. A lot is a good answer, but what's a lot? I mean, 10, 1,000? We're gonna do that today. It'd be easy. It's roughly 2.6 million. You want to play the lottery? You want to play the lotto? Cool. Now, depending which state you're in, it's usually between 50 and 100 million possibilities. But how would you count that? Well, you don't sit there and write them all down, right? There's a way to do the calculation really simply. You're a baseball manager. Well, how many people are on a professional baseball team? Is it like 25, is it? 26? I'm a professional manager and I want to put my starting lineup out there, my 9 people. You know, how many ways could I do my starting lineup? If it's 26 people, I'm going to calculate for you. It's about 1.1 trillion. That's how many different lineups the manager can put out. Wow, they should get paid more. It's about 1.1 trillion possibilities. I just calculated that in 2 seconds on my calculator.
How'd you calculate that?
How'd you calculate that?
You're going to learn that today. That's what combinatorics is. How to do big calculations. By the way, do it correctly without worrying about the minutia of like writing down every possibility. Something as simple as playing cards. There's too many possibilities. You don't write them down. What you do is you count them. So the idea is, first of all, I have a certain number of items, so we have to kind of get the idea of what's going on. Let's say I have 5 different books. I have 5 different books, and I want to arrange them on my shelf. Make it simple on yourself. Call it books A, B, C, D, and E. So do you agree that A, B, C, D, and E, that would be one ordering of my books? What if I said, you know, I want to switch the first 2 and keep the other 3 the same? Is this the same ordering, or is this a different ordering?
Different.
Yeah, every time something's moved, it is a different ordering. If I asked you exactly how many ways could I order the 5 books on my shelf, well, here's an easy way to think about it. How many choices do I have for the first book?
5.
5. There's 5 books. Now, I've selected my first book, and now I need to match it with a second book. How many choices do I have for the second book?
4.
And the third book? I kind of see a pattern here. 2. So if I said exactly how many ways could I put 5 books in order, it would be 5 times 4 times 3 times 2 times 1. That's it. And how big is that number? That's 120. Wow. By the way, do you want to write down all 120 orderings of A, B, C, D, and E? Oh, heck no. It'd take way too long. By the way, do you think you might miss 1 or 2 of them if you were trying to write them all down? Yeah, isn't it more important to know that there's 120? Garbage day today, I guess. Would you mind, Alicia, would you mind closing the door for right now? I hate this. This always seems to happen, you know, in something really cool and then boom, boom, boom. Okay, so what is this number? Does anybody, 5, 4, 3, 2, 1? Go back in your ancient history of math. We call it 5. It's math for the hearing impaired. 5, right?
Oh, factorial.
Good. Yeah, that was a joke. Bad joke. 5 factorial. Now, everybody on your calculator, let's find the factorial key. It's the one that looks like an exclamation point. This is going to be a really important key for us. I want you to find it because part of what today's all about is can you enter it correctly into your calculator. By the way, entering a number in correctly, there's kind of no forgiveness for that one because you got to do it correctly. There's not options there. So 5 exclamation point, do you get 120? Everybody cool with that? Now, if you have a calculator where you have to go through menu options, go to the highest point on the building and then drop it off the edge because that is an utterly worthless calculator. It will not help you and you will get the wrong answer if you get an answer at all. Mostly you'll get error messages. Yeah, this should take literally 2 seconds on any calculator. There's nothing, you get 5 exclamation point equals kind of thing. So it's flashing. Oh, you have a crappy calculator because you have to go through this entire menu options. Now, if you have to go through menu options, I'm telling you right now, don't use that calculator because I can't help you during the class. I can't help you during the lecture to go through the menu options to do a simple calculation. And that's all we're going to do is these simple calculations, but you're going to need help to do every one of them. Okay? If you have a PRB key, that means you have to go through a series of menu options. And there's nothing wrong with that. It just takes a really long time. And I found people get error messages more often than they get answers because they've unfinished business. Yeah, I have some cheap calculators you may buy with collateral, and I will bring these for the exam. These are probably the most user-friendly calculators I know of. They're about 15 years old. They were less than $10 15 years ago. So they're practically free now, but they're really nice, simple, and cheap. And the factorial key, you see it right there on the front. So go ahead and just use that one as your collateral. Because I need this to be easy.
We do it for collateral.
Anything. No, yeah, ID. The reason the collateral is I do want them back. When I do this during exams, a lot of people think they're parting gifts. Like if you were on a game show, I get to leave with the calculator. No. Remember I've been talking for the last 3 weeks saying you have to have a calculator you're utterly comfortable with? I have a graphing calculator, and those are awesome for graphing. That's what they're for. They're not for calculating, they're for graphing. So every time you want to do a simple calculation, you have to go through menu options. I'm too impatient to go through menu options. I want it right on the front of my screen to make it easy on me. Now, if you're comfortable using your graphing calculator, then use it. But again, I am not going to teach you how to use your calculator during the class or during the exam because there's 30 of you. Right? If you're going to use that calculator, that's a calculator. No, just put it on the side. Okay, so what is a factorial? In general, if I said n factorial, that means n times n minus 1 times n minus 2 all the way down to 3, 2, 1. So if it was 10 factorial, it's 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. If it's 2 factorial, it's 2 times 1. What if it's just 1 factorial? 1. Then it's just 1. It's actually that simple. Let's do 10 factorial. Of all of the functions that exist in mathematics, factorials are the fastest growing functions. And our technology is actually extremely limited. So, what do you get when you do that?
3,628,800.
620.
8,000.
8,000.
800.
So 8. That's a lot. What would that mean? I want to put 10 different things in order. I have 10 people. I have 10 books. I have 10 things. By the way, why do they have to be different things? I have 10 ping pong balls. I want to put them in order. If I rearrange them, will you note the difference? No. So when it comes to 10 ping pong balls, there's only one answer, isn't there? No matter what you do, it will always look exactly the same. But if it was 10 people, and I swapped 2 of you out, it would look different, wouldn't it? I can clearly tell you're being first in line, you're being 5th in line, you're being 10th in line. That's a different arrangement. So the simplest way to think of a factorial, it's the number of arrangements of that many objects. Arrangement means I'm putting them in order. By the way, there's going to be times when order doesn't matter. But if I'm putting things in order, there's exactly this many ways. So if I had 50 objects and I want to put them in order, it's 50 factorial. That's it. Now, that's pretty simple. Now, why did I say your technology in general is extremely limited with factorials? All right? On your calculator, do 69 factorial. I mean, 69 things. I mean, you know, there are big numbers, right? The distance to the sun is a big number. 69 is not a big number. But 69 factorial, when I do it on my calculator, what does your screen say?
Like,
Approximately what?
1.71, there's a bunch of numbers.
like,
Up to the 10th power, yeah, up to the 98th, yeah.
It gives you a scientific notation answer. Now, this is statistics. We're not, scientific notation is what you use in chemistry and physics for astronomically large or infinitesimally small numbers. In other words, astronomically large literally means you're talking about distances to planets and stars and things. Infinitesimally small would mean, you know, the mass of an electron. We need scientific notation in those situations because the numbers are so ridiculously big or so ridiculously small that we might not want to write out all the digits. It's a practical thing. You remember doing it in science class. I've been teaching math for a million years. You don't use scientific notation in math, ever. Literally, ever. There's no problem I've ever done in a math class where scientific notation made any sense whatsoever, yet I don't have access. There are 98 digits after the 1. That's a lot of numbers. Now, 70 factorial. 70 factorial is on the order of 1.2 times 10 to the 100th power. If I multiply this number by 70, and what does your calculator say when you entered 70 factorial? It says error. What, did you hit the wrong button? No. It's too big for your calculators. Wait a minute, 70? I want to put 70 things in order, and my calculator is now telling me that's not possible because it's too big for my calculator. 2-digit exponent, 3-digit exponent. Most calculators won't go past 10 to the 99th power. Now, I have a TI 89 titanium. I can go up to 449th power. Or 400, I'm sorry, I can go up to, 449 factorial, which is on the order of 999th power. But it's only 449. You know, in a world where infinities are common, 449 is not a very big number, is it? 69 is a really small number, isn't it? So when it comes to factorials, our technology is extremely limited because of how fast they grow. So sometimes we need tricks. Sometimes we need tricks to be able to do things. I'm going to show you some tricks because sometimes you have to do a calculation, but you might not be able to with the technology you have. Well, what about the supercomputer at UCSD? I heard it can go up to 1,000 factorial. The highest technology in human history can go up to about 1,000 factorial. But there are numbers that are a lot bigger than 1,000. 1,000 is not a very big number when you're talking about big numbers. You know, the sun is really far away. That's a big number. 1,000 is not a big number. So if I said 5 factorial, question, is that true? It was 5, 4, 3, 2, 1. Is that true? I'm showing you a trick that you can do sometimes to manipulate factorials. Okay? Because factorials don't just show up in this context. Most of the time you see factorials, most of them, they show up in quotients. Like factorial on top, factorial on the bottom. Okay? I would like to do the following problem. I would like everybody here to do, let's say, 50 factorial over 49 factorial. And let's use our calculators. So when you do 50 factorial, you get something really, really, really big. Am I right?
yeah.
And then divided by 49 factorial, you get something really, 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 really big. And then what's your answer?
50.
50. Huh. Could I have gotten that without using a calculator? Have I got an idea based on what I just said over there? What could I have done? You're nodding your head. Isn't 50 factorial the same as 50 times 49 factorial? And since it was all over 49 factorial, could I do that? Is that legal? Yeah, that's exactly what you'd want to do. Now, is the 50 pretty obvious? Oh, yeah, okay. Well, but I didn't need to do that because my calculator did it for me. You're right. You didn't need to do that. Your calculator did it for you. So let's do another problem of that nature. All right, I want to do 200 factorial over 199 factorial. Let's just use the calculator. So, so 200 factorial divided by 199 factorial, and is there a problem? What does your calculator say?
Error.
Why?
Because it's too high.
Because 200 factorial is way too big. Oh. In other words, your calculator can't do this one because both numerator and denominator are just simply too big. But isn't 200 factorial simply 200 times 199 factorial? And therefore, what's my answer?
200.
200. Didn't need a calculator, did I? Now, I'm showing you a trick that is useful when you can pull it off. In other words, when you don't actually have to use the calculator, this is easier to do this. Can we go ahead and open up the back door again? I think they're done with the, well, actually, what they do is they station a person there, and when they see the doors open, then they start banging things and stuff, and right now they're taking a lunch break. When they used to do construction on the tall building right there, we used to laugh because there'd be a person there, and I think they weren't doing construction, they just had a boom box with a recording. You know, you can buy, like to help you sleep, you can buy the sounds of like, ocean sounds. You know what I'm talking about, right?
Mm-hmm.
There's construction sounds you can buy, I guess. And so I'm pretty sure, because every time we'd open the door, it'd be construction noise, we'd close the door, it'd stop. We'd open the door, construction closed. I'd have her just stand there, construction, stop. And it was like a joke. Like there's somebody out there signaling, okay, start again. And it felt that way. Went on for a long time. I taught the GRE math portion at San Diego State for a few years. And I mentioned this to you guys before. The GRE it's like the SATs for grad school. It's called the Graduate Record Exam. And it's algebra, geometry, and statistics. The calculator, some of you may have used one of these calculators. You take the test on a computer, and on the computer screen there's the little calculator in the corner that adds, subtracts, multiplies, and divides, and doesn't have order of operations. Therefore, you can literally only add two numbers, or only subtract two numbers, or only multiply two numbers. You can't do a sum and a product because you're going to get the wrong answer most of the time because there's no order of operations. So is it a worthless calculator? Total. How many took a placement exam to get into Mesa? Did anybody do that? It used to be that you had to do the same thing in Mesa. You went to the computer and you took an exam for math and English so they would place you in a class. Nobody had to do that?
No.
Pre-pandemic, everybody had to do that. And they gave you a little calculator on the screen, same calculator. In other words, so if there were two numbers that needed to be multiplied, you could multiply them on the cheap calculator. You didn't have to do it in your head, but you couldn't do a whole lot. Well, on the GRE exam, they have a lot of factorials. Now imagine you are doing a lot of factorials and you don't have a calculator that actually can do a factorial. Remember, add, subtract, multiply, and divide. So one of the questions on the GRE would be something like this. I've got 6 factorial times 4 factorial over 3 factorial times 2 factorial. You say, well, I'll just use the cheap calculator and go 6 times 5 times 4 times 3 times 2 times 1, and then I'll write that down. And then I'll do 4 times 3 times 2 times 1, and then I'll write that down. And you're going to spend several minutes doing this problem, aren't you?
Mm-hmm.
And probably still get the wrong answer in the end. Is there something I can do that would make this easier? Remember, you can multiply in the calculator. Well, could I do something like this? 6 times 5 times 4 times 3 factorial. 4 times 3 times
2 factorial.
2 factorial. Would this work? Now what do I want to do with the factorials? Cancel them. Because it's a product, I can do this. Now can I use the crappy calculator on my screen to multiply those numbers? Yes, I can. And I would get the right answer fairly simply. This is the kind of math I would show people how to do, because this is the kind of question that would come up commonly on this GRE. And you're saying, but how am I supposed to do this? I don't get to use a real calculator. But that's understanding what a factorial is. So a factorial is just a sequence of products all the way down to the number 1. Okay? You can't have a fraction factorial, decimal factorial, negative number factorial. Only positive integers factorial. There is one exception. Some of you may remember this. On your calculator, enter 0 factorial. What does your calculator give you back? 1. That's weird. There is a reason, and we're going to explore that, and we're going to see why it's 1. 0 factorial is actually equal to 1. You're not multiplying by 0. No. Factorials, 5, 4, 3, 2, 1. If a factorial ended with 0, then wouldn't all factorials equal 0? Because you'd be multiplying by 0? No, you're never multiplying by 0 with a factorial. That doesn't make any sense. You're ending with 1. But 0 factorial is sort of like set aside. It's special. The calculation for 0 factorial is actually equal to 1. And I'm going to demonstrate that today. We're going to do some examples, and you're going to see why it is equal to 1. Okay? It's a strange thing that it would equal 1. But that does make my life easier. If I see 0 factorial, I know that's equal to 1. If I multiply by 0, what do I get?
0.
I get 0. You're not going to be multiplying by 0. That's not going to happen. But 0 factorial actually does come up a lot. Strangely enough, it does come up. Okay? Think of it another way. It'd be like saying, I want to pick one person from this class. Let's say there's 30 of you sitting here. I want to pick one of you. How many ways could I do that? Clearly, 30 ways. Do you agree? There's 30 ways I could pick exactly one of you. I've decided not to pick any of you. How many ways can I do that? One way, and that's not to pick any of you. That's basically what 0 factorial would represent. Not picking any of you. You wouldn't say there's 0 ways I could do it. No, there's only one way I can not pick any of you, and that's none of you. Does that make sense? So we kind of work our way up. So a factorial is this. And again, the number one use of a factorial is n factorial represents how many ways you can arrange n distinct objects. Why does it have to be distinct? Well, I have you and I have 9 of your clones. And you all decided to dress the same today, by the way. And now we want to put you guys in a line. Would we consider you distinct objects? No, we'd consider you identical. We can't tell you apart. So from the appearance, I can only see one way of doing it, because no matter how I arrange you, it's always going to look exactly the same, isn't it? So that's why we say distinct objects. That means things I can tell apart. That's why ping pong balls are a lousy example, because they all look exactly the same. But what if I took a bunch of ping pong balls and I painted every one of them a different color? Now would they be distinct objects? Sure. That makes it a little clearer. Okay, so n distinct objects put in order, n factorial ways. That's it. And if the factorial is too big, you start getting scientific notation types of answers. I'm not really worried about that. That's just representation. But the ability to calculate it using a cheap calculator is awesome. It's so ridiculously fast. So now, let's consider the following. We want to do a large count. Okay, let's start with something simple like phone numbers. All right, let's go back a long time ago. Let's go back to the 1940s, 1950s, when there weren't so many phones. How many choices do you have for a digit in a phone number? How many choices?
7.
Any particular digit, how many choices do you have?
10.
10. Yeah, people forget the 0, right? 0 and then 1 through 9. Do you agree that you have 10 choices for every digit? If I don't put any restrictions whatsoever on a phone number, and you just were having fun and you wanted to make up a phone number, how many phone numbers could you come up with? Well, if you have 10 choices for each digit, wouldn't it be this? Now, keep it simple. Do you actually have 10 choices for the first digit? Probably not. What can't the first digit of your phone number be? There's 2 numbers that it cannot be.
9 and 1.
No, not 9. 0 and 1. Oh, because what does 0 mean?
Operator?
Yeah, operator. What if you hit 0 twice? Any military folk here?
Stopper?
That's international operator. Oh, Now, if you hit 0 twice, that means you're now calling outside the country. Okay, so the first number of your phone number can't be a 0 because a 0 will do something else. And the first number of your phone number can't be a 1 because what does 1 do? It says, no, I'm going to do area code and all that. Okay, so let's have some fun. If there were no restrictions whatsoever, wouldn't this be the number of phone numbers? And this is 10 to the 7th power, which is 10 million. Wow, there's 10 million different possible phone numbers. 10 million phone numbers. There might be 10 million phones in San Diego County alone. What about the rest of the state, the rest of the country? Oh, that's not enough phone numbers, is it? So what was added way after the fact? I mean, there was a point when there was only 7 numbers. Then what did we have to add? Area codes. Exactly. And what did area codes then do? Let's assume, again, I just said let's assume there's no restrictions right now. Whoa, now it made it 10 to the 10th power. That's 10 billion. So we're probably in pretty good shape now, agreed? We went from 10 million to 10 billion. I think we're probably okay, except that we don't have, or do we? Do we have 1,000 different area codes? Yeah, we probably have a lot. I don't know if we have 1,000, but California alone. I mean, heck, San Diego County alone has how many area codes? 858, 619, 760. LA County has a lot more than we do. So maybe there are. So we're probably okay here. We're probably okay with this. Okay? Do we need more phone numbers? Probably not. So let's just have some fun. And you want to make up a phone number. And you know, you've been working on this for a while. You're looking at the letters and numbers and you want to spell a really cool word or just, whatever. And you decide, you know what, I don't really care. The only thing I care about is I want a phone number where I don't repeat any of the digits. Would that be hard to do? To have a phone number where you don't repeat any digits? How many here have a phone number with at least 1 digit repeated? Don't think area code, just your phone number. Okay, does anyone have a phone number without any of the digits repeated? That's kind of unusual, isn't it? So I want a phone number. So my phone number is going to be 987-654. That's boring. My phone number is going to be 123-4567. That would be a number where nothing's repeated. If I don't repeat any of the digits, then how many phone numbers are possible? No restrictions again. We're in an artificial world here. We're making it up. Well, obviously there's 10 choices for the first 0 through 9. But if I don't repeat digits, then what's the next one? 9. Then, So the product of these numbers would be how many phone numbers I can have if I don't repeat digits. So let's calculate that, shall we? All right, I got a number, but it only took me 3 seconds because I know a shortcut. You're going to want a shortcut too. What do you come up with? Anybody?
604,800.
When we had no restrictions, we said there was 10 million. Now we're down to 600,000, so that really made it smaller. Now, you just did 10, 9, 8, 7, 6 on your phone, or excuse me, on your calculator. That was a pretty simple calculation. Boy, wouldn't it have been way cooler if you could have just hit 10 factorial? I mean, that kind of looks like 10 factorial, but it's not, is it? Why is it not 10 factorial?
Because it ends at 4.
Because I don't have 3, 2, 1. Can I just do that? If I do that, I can. If I multiply by 3 times 2 times 1, and then I divide everything by 3 times 2 times 1, did I change the number? No, because that's equal to 1. Why would I do such a crazy thing? Because now what's my numerator? What is my numerator now? Isn't it 10 factorial? And I have a denominator now that's 3 factorial. Try that on your calculator. Do 10 factorial divided by 3 factorial. Do you get the same number? But a lot faster. Do you like that better? Yeah. This is actually a formula we're about to learn, okay? We're putting things in order, right? The digits 0 through 9, that's 10 things, and I'm putting them in order, but I did not use all 10 of them. I didn't use all of them, I used some of them. I used most of them, but I did not use all of them. What happens, I want to take everybody in this class, and I want to put 5 of you in order, or 10 of you in order. If there's 30 people here, putting 30 of you in order, I know it's 30 factorial. But I only want to put some of you in order. Can I do something like this? Yes, I can. Now, the word order has everything to do with things. When you're standing in line, it's a long line and you're the second in line. That does matter to you, doesn't it? You don't want to be the 200th person in line. You're second in line. You earned that spot. So in being in a line, clearly the order makes all the difference in the world where you are. But if I just said, I want all you guys, I want you people to come with me. I'm not putting you in any order right now. I'm just, sometimes just randomly grabbing. If I put things in order, the word order means I'm arranging you, okay? Arrangements. So when we ask how many arrangements of something, there's another word that means the exact same thing, but it's a mathematical word. The word arrangements also means permutations. Most everybody has heard this word used in the English language. I hate to tell you, but most of the time we've heard it used, it was used completely incorrectly because the person using it had no idea what it means. The word permutation means arrangement. It's exactly, they're synonymous. But in math we use the word permutation, and permutations refers to how many. How many of something. So if I said how many permutations, that's how many arrangements, that's a number. Okay? But when I hear people use words like permutation, they're usually using it completely incorrectly because they had no idea what it means. It's a lot of syllables. And when you use a lot of syllables, you sound smart, don't you? Especially when you mispronounce it, Permutations and arrangements are the same thing. So if I said, I want you to create a 7-digit phone number, by the way, does the order of the numbers in the phone number matter? Let me take your phone number and do it in reverse order. Will I reach you? No. Does your phone number, the order of the numbers matter? Yeah. Because if you get anything out of order, you're going to call somebody else. So the order of your phone number absolutely matters. How about your social security number? Does the order of the numbers matter? Yeah. You rearrange it, it's a different social security number. Everybody understand? There are a lot of things where, yes, absolutely matters what order. Your license plate, does it matter what order the symbols are? Yeah. Okay, so kind of get a clue here. So if I said how many arrangements, I had the numbers 0 through 9, that's 10 values, and I arranged 7 of them. But I don't see 7 in the denominator. What do I see in the denominator? What if I wrote it like this? Oh. Do you see where the 3 came from? It's 10 minus 7. Now, I listed everything down. That's nice. I don't want to list everything. I don't want to list everything down. Let's go back to the baseball example that we did earlier. All right? All right, you said there was 26 people on a baseball team. I want to create a batting order. By the way, does it matter if you're on the team and you're going to play today, does it matter where you are in the batting order? Yeah, it's called a batting order for a reason. Being first is different than being second, which is different from being third, and so on. That's why it's called a batting order. Could we call it a batting permutation? Sure. So, the Padres manager has to come up with today's lineup. 9 people are going to play, and they're going to be put in order of the batting. So if I said, how many ways could I do this? Is it 26 factorial? No, because all 26 people are not playing. Only 9 of them are playing. So let's do what we just did here. What would the answer be? It'd be 26 factorial over 26 minus 9. Perfect. Which is the same as what? What's 26 minus 9? try that on your calculator. This is the answer, by the way. When I did it earlier and you asked, how did I do that? Now I'm showing you how I did that. So you have 26 people, you're going to put 9 of them in order. So it's kind of like this. Let's say you're the Padres team right in front of me. And I'm going to pick 9 of you out, and I'm going to have you stand in a particular order. We don't even have to play baseball. You can be waiting in line at the grocery store. I'm going to pick 9 of you out, and you're going to stand in a line in order. This is how many ways we could do that. Now, 26 people? That's not a big number. 9 people? That's not a big number. And what do you have on your calculator? Something on the order of 10 to the 12th power. That's a trillion. 10 to the 12th power is a trillion. So you have an answer that's over a trillion. Does that seem kind of crazy? Outrageous? No, it's correct. I'm going to show you another way you could think about this. You're going to put 9 people in order. How many choices did you have for the first person? You had 26. How about the second person? 25. It'd be the same as multiplying 26, 25, 24, 20, all the way down to here. Now, this took a little bit of work on the calculator. Turns out there's actually a key on your calculator that will do this even faster. Okay, so let me explain what the formula is so you know how to enter it in your calculator. Permutations are a beautiful thing, and they're really easy to work with. So if we say we have n distinct objects, people, if you're a person, we're calling you a distinct object, because it could be I have books on the shelf, I have toys in the closet. I have n distinct things. People could be the things. You're going to choose R of them, and in parentheses, R is less than or equal to n. It can't be more. I can't have 26 people and I'm going to choose 30 of them. That doesn't make sense, does it? But I could choose 20 of them. Could I choose all 26 of them? Sure. I could choose all 26. That's not a problem. I'm going to choose R of them and put them in order. Then the formula that we just figured out is n factorial on top and n minus r factorial on bottom. But on your calculator, you have a key that does this. Some calculators, it looks like this. Some calculators, it looks like this. Some calculators, it looks like this. Find the capital P on your calculator. Okay? Now, on the cheapos that I just did, it should be on the main functions is probably above the capital C. You see it? Capital P. So, on your calculator, find the capital P, and let's enter. We're going to do this problem right here. You're going to enter 26 people. I'm choosing 9 of them. 26 P 9 equals. You get the same number? Then you know you did it right. Isn't that better? That's way better than entering all these little small numbers. This is called your permutation key.
What was the number? What's the answer?
What was the answer, guys? It was something on the order of 10 to the 12th power.
1.13 to 10 times 10 to the 12th power. It's like a long.
That's not what they got.
We'll try it again. You did or did not? Yeah, there's not a whole lot going on. You got to enter the right numbers. Now, the physical calculation, if you wanted to do it by hand using factorials, is this. This is way faster. So if I'm choosing R things, my denominator is n minus r factorial. I have 10 digits. I want to select 7 of them. So if you do, by the way, let's go back to this problem. Do 10p7. I have 10 objects. I'm going to choose 7 of them. Do you get the 604,000 when you do that? Hopefully you do. Then you know you hit the right buttons. If I want to do it the long way and write it out, I always can, but the danger of writing it out the long way, you might exceed the capacity of your calculator really, really quickly. Ooh, okay. Here's one of the beautiful things about your calculator. All right? You have 100 distinct objects. I want you to choose 5 and put in order. That means it's a permutation. So in terms of the calculator, if I just wanted to do the factorial, what's the answer? It's 100 factorial on top, and what's on the bottom? 100 minus 5, or 95 factorial. So do that on your calculator. We already know what's going to happen. It's going to say error, because 100 factorial is too big, 95 factorial is too big. What you failed to do was ask your calculator nicely. How can I ask my calculator nicely? By asking my calculator to do 100p5. And what does your calculator now say? Does it say error? Nope, it gives you the answer. I would rather you use the permutation key than the individual factorial keys. Using the individual factorials is always correct, but you see the problem? If the numbers are too big, the individual factorials you may not be able to calculate, but you can still do excuse me, the permutation. So what answer did you get? It was huge.
9 billion.
34 billion.
Oh, yeah, trillion.
So it's what? 9,034,502,400. Oh, that's a big number. It didn't go scientific notation. It wasn't quite that big. My answer's over 9 billion. Well, I have 100 things. I want to grab 5 and put them in order. Yikes, because the answer would be 100 times 99 times 98 times 97 times 96. That's your answer, if you want to do it really the long way. These numbers grow ridiculously fast, but you don't have to keep track of them. You got one of these. This is like, your 6 gun. Whoop. For effect. Wow, I've never done that before. That was cool. I got to remember that one. Okay. Trust the calculator once you learn how to enter the numbers correctly. Right off the bat, when you see a number like this, does it make you feel like you did something wrong because it's so ridiculous? Most people say, it's too big. No, there's no such thing as too big when it's factorials. Okay? The one thing we want to avoid is any calculation that produces an error message on a calculator, because then we can't continue. So in a problem like this, here's the question. This is absolutely correct. But our calculators are limited. They can't do that because numerator and denominator are too big. The trick I showed you earlier, could I do my numerators 100 times 99 times 98 times 97 times 96 times 95 factorial and cancel the factorials? Could I do that? Yeah. Why would anybody do that? Because somebody could have a calculator that is so old and cheap that it doesn't have factorials or permutations on them. I have people in classes all the time. They have a really ancient calculator and it doesn't have the factorial key. But I can still do the calculation by being smart and canceling things. Does that take a lot longer? Yeah, I'd rather do this. It's way faster. So understand, because factorials grow so big, that there are restrictions and limitations on your calculations if you're not careful. The moment you have anything bigger than 69 factorial, you already know your calculator is going to give you issues. Okay? Quick question before we move on. Yeah.
So if we were to do the 10 times 8 times 9 times 8 and then get rid of the 7 factorial, right, in this problem?
Well, it's 3 factorial actually.
Oh, okay. Maybe that's where I messed up.
It's 10 minus 7.
Yeah.
If you remember when we wrote this out, we wrote 10, 9, 8, 7, 6, 5, 4.
Mm-hmm.
Then we went 3, 2, 1 over 3, 2, 1. That's where the 10 factorial came from, and that's where the 3 factorial came from. So looking back, saying, how do you have 10 and 7 and get 3? Oh, 10 minus 7. That's why the formula, this is the formula, but I would rather you do it this way every time because it's so much easier, it's so much faster, and you can do things using this that if those numbers are too big, you won't be able to do it, but this will still do it for you. Okay, big P. Big P means permutation, which means arrangement. Now, in every conceivable scenario, does order always matter? Okay, how many here play cards? Any kind of cards. I don't care, it could be Go Fish. I deal your cards. What is the one where you start with 11 cards? Is it gin, is it rummy, or is it gin rummy? I can never remember because I know they're all different games. There's one of them. It might be gin rummy. You start with 11 cards and you're looking for straights and same suits. You're looking for all these different things and you throw one out and you pick one up. But you start with 11 cards. What does everybody do the moment they get their cards? You rearrange them in an order in your hand that makes it easier for you to interpret what you have. If you're a poker player and I dealt you an ace, card, ace, don't you move those aces next to each other so you can see them easier? Does that mean you now have a different set of cards in your hand when you move those cards?
No.
No. So does the order that you received the cards matter in that case? Or only the cards you received? We're going to form a stats class basketball team. But I'm only going to pick 5 of you. So I randomly choose you 5. Now, does it matter whether I chose you first, second, third, fourth, or fifth? No, it only matters that I chose you. Oh, so if I rearrange it, is it still the same 5 people? When they're introducing the starting lineup at the Lakers game, and maybe they introduce LeBron James last, is it a different starting lineup if they introduce him first? It's the same 5 people. So in that case, does order make any difference whatsoever? No, and it turns out that's the most common type of factorial problem, where order does not matter. Because if order does not matter, we would be way overcounting. So there is something called, this is the more common of the two, a combination. A combination is when I select the objects, but order does not matter. Because putting things in order means there's a lot more possibilities. If I took this group of 5 people and I put you in order, there would be 5 factorial ways of doing that. But if I just wanted to grab 5 people for the basketball team, my answer would be 5 factorial too big if I put you in order. But I just want 5 of you. I want to take 5 of you to lunch tomorrow. Does it matter what order you're chosen? I'm taking a group at one time. So if the order does not matter, and how do you know if order matters? If changing the order changes the outcome. Think of your phone number. Think of your social security number. Think of your license plate. If changing the order changes then order matters. But the cards in your hand, the 5 people I selected for the basketball team, if I change the order, does it change the outcome at all? Not at all. So when order does not matter, then the same, I have n objects, I'm going to select R. Okay? So n distinct objects. I'm going to choose R, and once again, R cannot exceed n, and order is not important. I'm only choosing the objects, I'm not arranging them. Then the answer is n factorial over n minus r factorial, just like before, with an extra r factorial. That r factorial was the putting things in order. If I have r things, there's r factorial ways of putting them in order, but that means I would have overcounted by that multiplier. This is called a combination. On the calculator, it looks like this, it looks like this, it looks like this, but the actual universal notation for this, believe it or not, and the notation we will also use, the big C is the calculator key. That's not the symbol people use in mathematics. That's the symbol on your calculator. Big C for combination. It actually is written this way. NR with parentheses around it. This is not a quotient, by the way. All of these things say the exact same thing. I want you to be familiar with this because all textbooks, by the way, this comes up in many, many, many different math classes. Some of you learned, maybe you did this in algebra class. This comes up in calculus. This comes up many classes, and this is the symbol that everybody uses. I'm not sure why we changed it, but this is the symbol. So Big C, this. If you, by the way, you don't have to use this, you can use this. But I will use this also in the notes or in the question, so you go, oh, that means combination when I write it that way. Question? Did I answer it?
Oh, no, it's type one, sorry.
Oh. Scratch your head. Okay. So, combination. Well, I asked you about cards a little while ago. How many cards are in a standard deck of cards?
52.
52. I don't need you to write them all down. That would take a really long time. I have 52 cards in a standard deck of cards. We're going to play poker. So of course, I have well shuffled cards. Always assume they're well shuffled. And then I'm going to, let's see, I'm going to give you a 3. I'm going to give you a 10. Does it work that way? I'm going to choose the card. No, I just shuffle them and I hand them to you. Now you're going to look at your cards. If one card is swapped out, that's a different set of cards. I chose you 5. You know what? I'm sorry, Terrence. I gotta replace your 5. Now it's a different set of 5, isn't it? It's not the same team anymore. So changing one thing is not the same thing. Okay? It has to be the exact same 5 to be the same thing. So if I said, how many? Okay, there are 52 cards in a standard deck of cards. You're gonna play poker. How many? And the term we use is 5-card. I don't know why we use this term. What do we say? 5-card hands. A poker hand is the 5 cards you're dealt. Why do you suppose we use the term hand?
It is
I'm guessing. Why do you suppose we call it a poker hand?
5 fingers.
Because you have 5 fingers on your hand. And there's 5 cards when you. I have a feeling that's probably why we call it a hand. Because a hand has 5 fingers, you got 5 cards. Okay. How about we just call it the set of cards you were dealt? Your poker hand. All right? Exactly how many ways can you be dealt 5 cards? This is exactly the same question as how many different poker hands are possible. The answer is 52, choose 5. So this is the formal math notation. When you go to your calculator, what are you going to do? 52C 5. And this number surprises the heck out of everybody. 2,598,960. I've done this problem about 1 billion times. I know that like my phone number. That's roughly 2.6 million hands are possible. Yikes. Do you want to write them all down, by the way? Oh, heck no. That would be crazy. That would be crazy. Now, I don't play poker. I don't find poker as interesting as I like playing blackjack because it's an easier game, but it's actually more mathematical and strategy. You know, I only have to do one card and over 21, under 21. It's blackjack to me. The strategy is easier, but it also is it's just more fun. It's faster. But you're a poker player, and you got to rely on 5 randomly selected cards and things like this. But the question people always have when you're a poker player is, I have 5 cards and I have pretty good things. You have 5 cards. Who wins? There is a hierarchy, isn't there? Best, not as good, not as good. I have something going on. Maybe I have 3 10s and then 2 random cards. And you have 4, 5, 6, 7, 8, 9. 4, 5, 6, 7, 8, sorry. Only 5 cards. You have what's called a straight. I have what's called a 3 of a kind. Who wins? Some people, they memorize it. How do you decide, if you're a poker player, who wins? What makes one set of cards better than another set of cards?
The odds of getting them?
Yeah. Basically, how many possible ways are there to do it? The more rare the hand, the more valuable the hand. If I just, for example, we're not going to do this today. I do this in my upper level classes, but we'll do the actual calculations. 2 of a kind means you have 2 of the same number and then 3 random cards that are all different. There's over 1 million ways of doing that, of the 2.6 million. So it is the absolutely least valuable hand. I have 10, Jack, Queen, King, Ace of the same suit. It means all clubs or all spades or all hearts or all diamonds. There's exactly 4 of those possibilities in a deck of cards. That's the most valuable hand. What is that called? Does anybody know?
Royal flush.
A royal flush. Ooh. Yeah, that's a cool name, isn't it? And by the way, what if, okay, I cheat at cards, I've got the little, the little deck dispenser in my sleeve, and so do you, and we both came up with the royal flush. Doesn't end in a tie, does it? Yours was hearts, mine was aces. Who wins? There actually is a hierarchy of aces are the highest, clubs are the lowest. I believe it goes aces, hearts, diamonds, clubs. Now, as silly as that is, of 2.6 million cards, we have the highest two possible. By the way, does that happen?
Spades is highest?
Spades is the highest, yeah.
Okay.
Spades is the, what's considered the highest card? Was there ace of spades?
Oh,
You've heard of ace, oh, okay, yeah. Ace of spades is kind of the universal, the highest card you can get in anything. That's why. It's spades are the highest. But the point being that everything's based on a calculation and based on probability of what is the rare. So if you were that poker player, you're like, oh, I got two aces in my hand and three other cards. So what you could probably do? Discard those, get three more, hoping you maybe get another ace in there. That's the strategy. But the point being, everything's based on probability of what is the least likely, what is the most likely. The less likely, the more valuable. In other words, the more rare, the more valuable. You don't ever have to worry about playing cards, but understand that that's how it works with cards. So you watch these things on TV where they're playing poker for money and and all this, and it's like, but it's so much luck is involved. You're right. I have to be dealt the cards. But once I'm dealt the cards, is there skill involved after that? Yeah, it's about making the best decisions based on likelihood and probability and things like that. Boy, I'd just rather be dealt a whole bunch of aces, it'd make my life real easy, then I don't have to use any strategy. Does that make sense? But that's probably not going to happen. So combination order isn't part of the calculation. So the combination number will always be smaller because you have this extra term in the denominator. Now, the only mistake people make is they do a permutation when it should have been a combination, they do a combination when it should have been a permutation. The simple rule is, if order matters, it's a permutation. If order does not matter, it's a combination. Now, I'm going to give you a simple way of remembering this because there is so much math in your life that you don't even realize. When I'm teaching calculus and above, I use all of the different situations. I mean, Dr. Seuss even had a lot of calculus. The Cat in the Hat had thing 1 and thing 2, which are your two independent variables in calculus 3 in 3 dimensions. And you can't prove the fundamental theorem of calculus without using the garbage pit scene from the first Star Wars movie when the walls are closing in. And I actually use these. Well, turns out the easiest way to understand this is pizza. Okay? Now, you're going to go to the pizza place and you're going to say, okay, I want pepperoni, sausage, black olive, green bell pepper. That's my favorite. In that order, I want you to put it on the pizza. And they'll go, okay. And after the cheese, they put all those things on the pizza. And by the way, what happens to the pizza? Everything melts and goes sideways. Would you know what order they put the ingredients on when you get your pizza? No, it's not possible. Why? Because everything went sideways. They're not vertically stacked. So you told me what order to put it on. I'm going to mess with you. I'm going to put it on in reverse order. And you got your pizza. Would you know that I put it on in a different order? No, you couldn't. That's why when you order a pizza with all sorts of things, the order they're put on does not matter. It only matters what order what items you chose. That's why when you're calculating how many pizzas, it's not called a permutation pizza. What is it called? A combination pizza. And by the way, that version of combination is exactly the same mathematical meaning of this one, meaning it only mattered what ingredients you chose to put on your pizza, not what order they went on your pizza. Because if I rearrange the order, it's still going to be the same pizza, isn't it? So that's the easiest way to remember. Think pizza. Combination pizza means I got everything I wanted, but the order did not matter when it was put on. Now, a permutation pizza. That'd be a strange pizza because that probably means I'm stacking my ingredients, right? I don't think that pizza exists. You with me on that? All right, now, you want ice cream. You want to get some ice cream. And I mean, I grew up eating ice cream cones. I never do cones anymore because I don't eat it fast enough. So therefore it just drips all over the place and melts. And so when I get my ice cream, I get it in a bowl. Pretty much every time. I do a bowl. I'm a bowl guy. You know, cones are nice. I'm a bowl guy. So I go to an ice cream parlor, and let's say there's 40 flavors of ice cream. And I want to choose, obviously, different flavors. I mean, you know, so you go to the ice cream parlor and you get, I want 3 scoops of vanilla. I mean, that's legal, I guess. Doesn't it just feel wrong? 3 scoops of vanilla. No, you want 3 different flavors, okay? So you want 3 different flavors. So you chose your chocolate and your mint chip and your, I don't know, what's another good one?
Rocky Road.
Rocky Road. Does it matter what order you chose them? When you get that bowl and you have 3 scoops sitting sideways, side by side, is there any possibility you could tell what order the scoops were put in? Actually, you can't.
You can watch it,
You can watch it, but when you're looking at the bowl, any order you put the scoops in, it would still look like the exact same bowl, wouldn't it? So when you're ordering those 3 scoops and say, I want these 3 scoops in my bowl, if I said, how many ways could we do this? Would this be a permutation or a combination? This would be a combination. So if I said, how many ways could you go to the ice cream parlor that has 40 choices of flavors, and you want a bowl with 3 different scoops in? So what's the answer? It's 40, choose 3. And what is that number?
9,880.
What I love is how fast and how simple. On most calculators, the C, the big C is the main key, the big P is the second. Does everybody know what I mean by second? Then you have to hit second to get the. Most calculators are not both. So 9, 8, wow, that's a lot of choices. I have almost 10,000 possible ways I could get a bowl of 3. Yeah, just for fun. You're a cone person. You can't help it, you're a cone person. So when you want your 3 scoops on a cone, and you say, I want the Rocky Road on the bottom, because as it melts, I want the nuts to fall to the bottom of the cone. You have some strategy here, right? And I want the chocolate on the top so the mint chip is kind of sandwiched between. I mean, I have a strategy when I'm building my cone. Will the order of the cone matter? Now, in other words, if I scoop in a different order, will you be able to tell? Yeah, because they're stacked. Oh, so if I said how many ways could I do a cone, would that be a permutation or a combination? Permutation. If it really mattered to you that Rocky Road was on the bottom and not on the top, then it would be a permutation, because rearranging the order, you could clearly see it being a different cone. Does that make sense? So, if I said it was a cone and you're stacking them and it does matter, you really do care what order they are, then what's your answer? It's P. By the way, the formal mathematical way, we really write it like this, but on your calculator, you're going to go 40P3. On your calculator here, you went 40C3. That's the order of buttons you're going to push. Okay? Always show, by the way, whenever you're turning in math work, always show this, because what happens is people will write the right thing, but they may hit the wrong button. Does this happen often? At the beginning, probably half the time. In other words, you wrote the right thing. You were correct mathematically, you hit the wrong button. But you're demonstrating, hey, I know what it was supposed to be, I just, fat fingers, hit the wrong button. That's an easy thing to fix. But if I wrote the wrong thing, that means I have the wrong idea. So always write what it is you're going to enter, because no one's doing this in their head. Some of you got my email, some of you have gotten a bad habit on problems. I asked a question the other day of variance, and I'm getting numbers. Variance is a very long calculation with lots of things in a quotient. If I'm getting a number, it tells me it looks bad. It looks like you got it from somewhere else and you didn't know how to get it, because nobody in their right mind would write a number that required a major calculation. No, you always show the numbers you're entering into your calculator. That's your justification of the answer. Plus, it's also your insurance. You wrote all the right numbers, but you hit a wrong button. Then you have a small error because you have the wrong answer, but you have the right numbers, you hit a wrong button. That's not a huge error. But not showing anything and having a wrong number, then there's no possible way to know where the number came from. What's the difference in answers if it's this one?
It's
59,208.
Wow, that is so much bigger. 59,280. This is about 6 times bigger than this one. It's exactly 6 times bigger, by the way, 3 factorial. Wow. Generally speaking, permutations are always bigger and sometimes a lot bigger than combinations using the same. So here's a different story. I'm going to pick 5 people for the basketball team. But I'm also going to take them to lunch. On Monday, we're going to go to Mr. A's. On Tuesday, we're going to go to Burger King. On Wednesday, we're going to go to that really cool Mexican restaurant down by the water. On Thursday, we're going to go to Anthony's Fish Grotto. And on Friday, we're going to go to McDonald's. When do you want to be picked? Maybe first? You probably don't want to be second or fifth. If I'm choosing the 5 for the basketball team, but I'm going to take you to a different, each person is going to go to a different restaurant each day. Now, does it matter what order I pick you? Yeah, you want to go to the good restaurant, not the bad restaurant. So can I take a situation and change it from a permutation to a combination or back and forth? By ordering or not ordering. So picking 5 for the basketball team, order does not matter, but I said, but each choice is going to go out with me to lunch to a different restaurant. So you still got chosen for the basketball team, but you want to go to the good restaurant. So now I just made it a permutation, didn't I? Does everybody see that? If order matters, it is a permutation. Okay? Everybody cool with that? All right. We're going to do something right now and practice. I need you to have your calculators, and I need you to be comfortable and competent. All right. We're going to do each calculation here. The 0 factorial, I'm going to demonstrate in a moment why it's 1, but I want to just go through this really, really quickly. Okay? So, if everybody can do this, go as fast as you want. This, by the way, if you have your computer, this is on Canvas. It's, what do they call it? It's called, actually, I think it's just called Factorial Worksheet or something like that. If you're having a hard time seeing, you can just go ahead and move forward a little bit. But I want us to do these and get used to it and hopefully get all the right numbers. If you can do these, there's no question that you won't be able to do in terms of calculation. It is a little small though, I know. So some of you might want to move up a little bit in your seating. Make this bigger. Oh, here we go. Oh, good. Okay, is that better? Okay, let's do this. I'll wait a couple of minutes and then I'll scroll.
Are we handing this in? Should I do
No.
it on a separate sheet of paper?
No. This is, I'm saying, can we do these? Yeah, no, you're not turning these in. There's like, let's do these and hopefully we get them all right. Okay. I'm still recording because I want to go over the answers as part of this. I have no doubt that everybody can get all of these, but since most of this is fairly new unexplored territory, it might take us a moment. Okay. Scroll down to the next. Everybody got these so far? Now, I'm going to think of the next 4 as a cluster. I'll leave it like that. 7, 8, 9, 10. So the first ones that were just straight up factorials. Now I want you to use your permutation key.
I have a question. I put it in my copy.
Are you having issues?
Yeah.
Are you having to go through menu?
No, I pressed the.
Oh, you forgot the factorial on top. That's why. You see it? You have an 8 rather than an 8 factorial, that's why. You had the right idea, you just grab the factorial. Yeah, now try it, it should work. All right, so far so good? All right, let's do the rest of these. And the rest of these are combinations. Oh, boy. A little bit small, I know. A little tight there. Okay. Everybody good? All right, we're going to talk about a couple of these guys now. Now, I mentioned 0 factorial. 0 factorial is a confusing one. I have a class of 30 people, and I want to take 5 of you to lunch at one time. Do you agree that the answer should be just simply 30 choose 5? And then I do that on my calculator, and I hit the C key, so it'd be 30, choose 5. Now, what is this as a factorial? This would be 30 factorial over 30 minus 5, 25 factorial. If I actually had to enter, I don't want to enter by factorials, it takes too long. I might make a mistake, I'd rather use that. But let me ask you a question. I want to take 5 of you with me to lunch. No, instead, I'm in a bad mood. I'm going to pick which 25 of you I'm going to leave behind. Rather than tell you which 5 I'm taking to lunch, which sounds very positive, you're staying behind, you're staying behind, you're staying behind. How many ways could I choose 25 of you to stay behind? Or would it be the exact same answer? Choosing which 5 of you to take with me, wouldn't that be the same as choosing which 25 to leave behind? So that means that this is equal to 30 choose 25. Huh. If those numbers add up to that number, it's always going to be the same thing. Does that make sense? Oh, okay. It'd be like saying, I'm going to deal you 5 cards from the deck, or I'm going to choose which 47 cards not to give you. That sounds silly, but wouldn't it be the same answer? Yeah. Now, There's 30 of you. I want to take all 30 of you to lunch. I got a loan from the bank. I got a checkbook. I wrote a check for $1 million. Of course, it's not backed by anything, but you know, I have a checkbook. I wrote a check. So I want to take all 30 of you with me to lunch. How many ways could I take all of you to lunch? Wouldn't it just be one way? Because I'm taking all of you. So what does that look like as a calculation? If I take 30 of you to lunch, wouldn't that be this? Now, we agree the answer is 1. We agree the answer is 1. There's only one way I can take 30 of you to lunch. Oh, by the way, I changed my mind. I'm broke. I've decided I'm not going to take any of you to lunch. How many ways can I do that? 1, and that's, I'm not going to take any of you to lunch. So do you agree that 30 choose 30 is the same as 30 choose 0? Yeah, it is. And they're both 1. As a quotient, isn't this 30 factorial over 30 factorial 0 factorial? Do you see why 0 factorial has to equal 1? Because if the answer is 1 and those guys canceled, that has to equal 1, doesn't it? 0 factorial equals 1, because 0 factorial represents literally the I didn't choose anybody, but there's only one way I could not choose anybody, and that's not to choose anybody. So a lot of folks will just say it's a definition, just memorize it. No, I'd rather you see it. You told me the answer was 1 in both cases. There's 30 people, I want to choose all of you, there's only one way. I want to leave all of you behind, there's only one way. But the calculation is 30 factorial over 30 factorial 0 factorial. And that can't equal 1 unless 0 factorial equals 1. So that's a simple way to justify why 0 factorial is equal to 1. So when you see 0 factorial, don't do a 0. In fact, don't even use your calculator. But you know, you got confused. Oh gosh, what was it again? Your calculator will give you the 1 every time. And then you go, okay, yeah, I know that's 1. Okay? Everybody cool with that? By the way, be honest. How many got all of them? Nice. Okay. Great to get all of them. There was one tricky one that potentially give us an error. Which one was that? Number 4. Because if you entered it as factorials, you got an error. So what did you do? 100 times 99 times 98 factorial, then you canceled the factorials. That was the trick. That's how you get around the fact that your calculator can't do big factorials, is you just cancel things. And you can always cancel things with factorials. That's one of the best parts about factorials mathematically, is they cancel so nicely.
Can you do 5?
8 factorial divided by 3 factorial, 5 factorial.
I got a different answer than you did, so can you walk us through
That means that you multiply it by 5 factorial. You have to use,
Can you just walk us through the problem?
but you have to use, starts with a P,
Permutation?
ends with an parentheses.
Oh, parentheses.
If you don't use parentheses, you're going to get the wrong answer on everything that's, no. You have to use parentheses because you have a product on the bottom. So when you're entering it, you can't hit times, otherwise you just put it on the numerator. You've got to, it's just like if I had a sum on the bottom, if I have a product on the bottom, if I have any stuff going on the bottom, you always have to have parentheses, otherwise your calculator doesn't know that that's what you meant. Now, you have a TI-80, you have the 36X Pro, right? Okay, when he was entering it, it actually put the numbers in the numerator and denominator, which I love that because the display is wonderful. It takes a lot longer to enter everything, but there's no way you're going to miss that problem because you could see it on your screen, couldn't you? So his calculator, when he entered it, actually entered it in this visible form. Most of our calculators won't do that. They won't show you, because we enter things linearly in one line. If you have a calculator that will show your input as a quotient, then you know if things are in the right place. If I try to do this, but I don't use parentheses around my denominator, then I'm always going to be moving that thing up and I'm going to get an incorrect answer and I won't know what went wrong. You know, that's what went wrong. Okay, can we go ahead and start recording?